Hi everyone, myself Bidyutlata Sahoo, working as an assistant professor in the Department of CSE, Artificial Intelligence and Machine Learning at Institute of Aeronautical Engineering, Hyderabad. In this video lecture today, I am going to discuss about the topic problem reduction on the course Applied Artificial Intelligence. These are the topics to be discussed. First, I will introduce what is the meaning of problem reduction and a few examples like how the problem can be reduced using AND or graph, and two classical algorithms we will use to introduce about this problem reduction technique. So one is the Tower of Hanoi problem and using Aeronautical algorithm. This is the topic learning outcome. After the completion of this topic, students can apply the concept of problem reduction in complex engineering or complex problem to break into smaller sub-problems using AND or graphs and search techniques. Okay, let me introduce about what do you mean by problem reduction. Normally, when a problem reduction means reducing of the problem into smaller sub-problems. Sometimes certain real-life problems which are extremely complicated and seems to be hard to solve. So what happens, an effective way of solving a complex problem is to reduce it to smaller parts and solve each part separately. So the problem is automatically solved when we obtain solutions to all the smaller and simpler problems. So this is the basic intuition behind the method of problem reduction. So problem reduction, what it says, we are reducing the problem. We have the complex problem. This complex problem will be divided into number of sub-problems, and each sub-problem will be solved separately to find out some solutions, and the solution of each sub-problem gets combined to find out the final solution. So this method is called as problem reduction. So why we are using the problem reduction? To solve the complex problem in artificial intelligence. Now, if you're looking for a sequence of action to achieve some goal, then one way to do it to use the state space search. Already I have discussed in my previous videos what is the meaning of state space search. The problem which is very small and it is easy to solve, then we can go for a small state space search with the help of nodes and using a tree structure. And we can explore the tree, means all the leaves of the node, to find out the path or the best possible path. So that is nothing but the state space search, where each node in your search space is a state of the world, and you are searching for a sequence of actions that get you from an initial state to a final state. Now, if you take the example of breadth first search or depth first search, so these two or depth limited search or any AO star search or A star search, any kind of informed and uninformed search related to the state space search, where the nodes will be explored, means nodes can be represented with the help of tree structure, means hierarchical structure, and all the nodes, each node is what it represents. It represents a state, and the complete collection of all the nodes in a particular space is called as the state space, and all the nodes or all the leaves of the nodes are explored either using any one technique, either informed search or uninformed search, starting from the initial state to the goal state. The goal state can be any state, it can be search. Either so different algorithms are there, like breadth first search. The searching technique happens like this, and breadth first search, it searches to its complete depth, then it backtrack and moves like this. So different techniques are used to explore the path starting from the initial node to the goal node. But in this case, in problem reduction, that we will not do. So what will happen? Another way is the goal state can be decomposed into simpler sub-goals. The problem reduction, especially, it is not used to find the path from initial state to the goal state. This type of problem reduction methods or techniques are used how to achieve the goal. That is why this technique is used in artificial intelligence. Then how to achieve the goal means what we have to do, we have to divide that goal or decompose that goal in simpler sub-goals first. Now here I have given one simple example you can easily understand. When planning a trip to Bangalore, you probably don't want to search through all possible sequence of actions that might get you to Bangalore. That means we will not say that we'll pack our bag, then we'll go to station, then we'll take an auto, then we'll go something, we'll do those, all these small things we will not take care. But what we will do, you are more likely to decompose the problem into simpler one, like such as getting to the station first, then getting a train to Bangalore. This is one method. How to reach the Bangalore, that is the goal of our task. So first we will go to the station, then we'll catch the train to reach the Bangalore. So this is one way, or else we can say some other way also it will be there. There may be more than one possible way of decomposing the problem. So this is an alternate strategy. We'll go to the airport, then fly to Mysore, then we'll catch the train to Mysore from Bangalore. So this is another way so that we can reach the Bangalore. So even there may be so many possible ways would be there, but which way is the cost effective as well as time effective, that is very important in case of the problem reduction. So these different possible plans would have different cost, means with respect to time and benefits associated with them, and you might have to choose the best plan. So problem reduction says that to achieve the goal state, there may be n number of possible solutions, but out of n number of possible solutions, which solution provides an effective solution, means with respect to time and cost. That is the main goal of problem reduction. Now, the simple state space search technique could be represented as a tree. Just now I have given the example how a simple state space search tree like BFS and DFS can be represented with the help of tree, where each successor node represents an alternative action to be taken. The graph structure being searched is referred to as an OR graph. If we draw this graph like this, means this is the root node is having 2 child, then again from this node 2 children, and again from this node 2 children, then each node is called as a state of the search space, and all the nodes can be represented with the help of OR graph, because either we'll follow this path or we'll follow this path to reach the goal state. It's not like at a time I cannot follow both left side and right side. That is why it is called as OR graph. In OR graph, we want to find a single path to a goal state. So if I'm searching from left side, then I may reach the goal state. Or else if I do not get this way, I may go the right way. I may not reach the goal state also if I move in the right way. So OR graph always gives the alternate solution. Either you follow this or that. But in OR graph, we want to find a single path to a goal state. But to represent the problem reduction technique, we cannot use the OR graph. We have to go for AND OR graph tree or AND OR graph, where 2 graphs will be there, means 2 structure. One is the OR graph as well as the AND graph. Now let me introduce what is the meaning of AND OR graph or AND OR tree. So as we know about the divide and conquer strategy, I think you might have known in mathematics, divide and conquer strategy, even in the data structure also, we used to divide the problem into smaller problems. So divide and conquer strategy, how it is solved. Here the solution to a problem can be obtained by decomposing into smaller sub-problems, and each of the sub-problem can then be solved to get its sub-solutions, and these sub-solutions can then recombine to get a final solution as a whole. That is why it is called as problem reduction. Just now I have explained at the starting of the video. AND OR graph or AND OR trees are used for representing this divide and conquer strategy or for this problem reduction technique. So normally this AND OR graph is used to find more than one solution. This point we have to remember always as the main problem. Our goal is how to achieve the goal. This goal can be achieved by dividing the complex problem into smaller sub-problem, and each smaller problem gets solved separately to find out the final solution. right? So this method, the final solution or the goal can be achieved in many ways. That is why it says the AND or graph can find more than one solution. This method generates the arc, which is called as AND or arc. One AND arc may point to in any number of successor nodes, all of which must be solved in order for an arc to point to a solution. So the meaning of the statement is this problem reduction technique can be represented with the help of AND or graph. Then how it looks like? If this is my goal, then this goal can be achieved either by following, either using this path, or else we can follow this path. If any arc is there between two paths, then this type of arc is called as AND arc, and this is called as OR arc. So OR arc means these are the solutions. So either you follow this OR arc to achieve this solution, or else you follow these two so that we can achieve this goal. So why both the sub problems are required needs to be solved? Because one arc is present. So AND means both the conditions should be satisfied. If it is 1 1, then only 1 into 1 it will be 1. The same thing here, the same rule applies. If both the conditions satisfied, then only we can achieve this goal. So either you follow this path or else you follow this path to achieve this goal. So there are two possible solutions, but we have to think that which path is giving the optimal solution, that would be the best solution we can say. But overall, this AND or graph in problem reduction technique gives more than one solutions. Now this is the example for me to make you understand how this AND or graph can be represented. Now the goal state is how to own the mobile phone, how you can achieve a mobile phone. So there are two alternate ways. One way is this one. Either you steal it from somebody, directly you can achieve the mobile phone, or else you earn money and buy the mobile phone. How you can earn money? That means you work hard, earn money and buy mobile phone. So two things are given. You earn money, then you buy the mobile phone. That means to achieve this mobile phone, we have to earn money and then only I can purchase the mobile phone. That is why one arc is given between this path and between this path. So either I'll follow this path completely to achieve the mobile phone, or else I'll follow this path so that even I can achieve the mobile phone without working any hard work. I can steal from somebody and I can achieve the mobile phone. So this is the way of representation for AND or graph. Now this AND or graph, it breaks the problem down into smaller sub-problems, and it can be represented using the goal tree with the help of AND or tree, because the root node here, it is the goal node. The main goal of the AND or tree is to achieve the goal. Here nodes in the tree represent the sub-problem, and the root node represents the overall problem, which is called as the goal of the problem. Okay, some nodes are AND nodes, meaning all their children must be solved. So these are the points needs to be remembered for AND or graph. Now I'll explain two classical examples how this problem reduction can be solved using Tower of Hanoi problem. So this is a classical example of problem reduction. So in the problem reduction space, the nodes represents the problem to be solved or goals needs to be achieved, and the edges represents the decomposition of the problem into the sub-problem. So this we can illustrate with the help of Tower of Hanoi problem. So this is the Tower of Hanoi problems looks like this. This is our initial condition and we want this result. So what the Tower of Hanoi problem says, here we have three pegs. One is the peg A, then peg B and peg C, and we have three discs, 1, 2, 3. These are three blue discs, and all the three discs are placed one over the other. Now our goal is all the three discs which are present on the peg A, it should be transferred to the peg C. So we want this result. So to how we can solve, and one constraint is here. What is the constraint? We have to follow that constraint always while solving this problem. the bigger disk should not be placed over the smaller disk. Means the bigger disk should not be placed over the smaller disk. So that constraint we need to take care while solving this problem. Now I'll solve this problem. So here first is there are three pegs. Three pegs are given. What are the pegs? A, B and C. So and three disks are given. Three disks are there. Okay, all are in blue color. Now all the three disks are present on the peg A. So here this is the initial state. So how we can, so first we will try to decompose this problem. So what is our goal then? We have three disks are there on the peg A. So all the disks should be transferred to the peg C. So it should be our goal state. So how to achieve this goal? So now we will divide the problem into sub-problem. First, what I will do, first we'll transfer this upper one and the second disk to the node B or to the peg B. Okay, so two disks we can transfer from A to B. Okay, then the last disk we can transfer to C, A to C. Then whatever we have two disks at B, we can transfer from B to C so that we can achieve this goal state. Now you check the constraint. I told the constraint is for this tower of a problem, the bigger disk should not be placed over the smaller disk. This is our constraint. So is it satisfying? Whenever I'll transfer the first smaller disk and the middle one from A to B, what will happen? Smaller one will come here, then the bigger one will come here, right? Though we have transferred, so this one is not satisfying, means we cannot achieve to AB. So again, we have to divide this problem. We have to solve this problem first to AB. How to solve? So what we will do, the smaller one from A, first I will transfer to C, okay? Then from A to C. Now the second one, which is in A, that I will transfer from, that means one disk, the middle one, I'll transfer from A to B. After transferring the smaller one which I kept over here, then I can keep it over here. Then one from C to B. Then I hope we can achieve this goal to AB for the time being, because these are the sub-problems. These three are the sub-problems to achieve the goal state. But each sub-problem should be satisfied by using this constraint, whether it is satisfying or not. But this one initially it was not satisfying. So again we divided this task like 2AB, which is there, which does not satisfy the constraint. So what we'll do, the smaller one, let me erase so that you can understand. The smaller disk will be transferred to C first, and the middle one will be transferred to B. Then the smaller one will be transferred to B, so that the constraint will be satisfied as well as our condition also. Okay, and we achieved that to AB. So this is what the solution for 2AB. Now you check the second sub-problem, whether it is satisfying the constraint or not. So the last disk which is present over this peg A, the last disk we are transferring to C. There is no issue. So this is also satisfied. Now you can check this one. 2BC means now after this operation, how is our condition? This means bigger one, the middle one is on the peg A, then the smaller one is on top of the middle one. Now if I transfer to C, what will happen? The smaller one will come first and bigger one will be over the smaller one, which again does not satisfy the constraint. So what we will do? So to achieve 2BC, so what will happen? The smaller one, okay, the smaller one which is present on this, okay, let me draw this one. First is bigger one, then smaller one. The smaller one I can transfer to A first, then this middle one, already our middle one's 1AC, when we did this operation, the last disk which is present over here, already it is there on the peg C. Now the smaller one which is present on the peg B, you transfer to the peg A. So what we'll do, one from B to A. After that, the middle one which is there, that I can transfer to C, means one from B to C. After this, the smaller one which I have transferred to A, that will transfer to C, 1A to C. I hope using these three solutions we can achieve this 2BC. So this is our final. Now this one is achieved, this one is achieved, this one is achieved. So definitely the final goal is also achieved. So this is the way the Tower of Hanoi problem can be solved by using the problem reduction technique. So here the nodes in the graph will point both down to its successor. Now, okay, sorry. One more algorithm is there. Problem reduction is there. Just now I discussed. One more technique is also there, that is AO star algorithm, that is also used to handle the problem reduction. So here in AO star, what is the meaning of AO star algorithm? A stands for AND, O stands for OR. So here AND OR graph we will use to solve the problem reduction technique. So here node in the graph will point both down to its successors and up to its parent node. And each node in the graph will also have a heuristic value associated with it. What is the meaning of heuristic value? Heuristic value normally we used to denote with the help of small h or capital H of the node n. That means the distance from the current node to the goal node, that approximate distance is nothing but the heuristic value. So this is what to understand the AO star algorithm, I kept this picture. Because one of the function here it is used, that function is called as the cost function, which is denoted as f of n. We have to find out the cost of each node. How to find out the cost of each node? So this is what the formula is. F of n is equal to g of n plus h of n, where g of n is the actual cost and h of n is the heuristic cost. Actual cost, suppose our current node is at this place n, then the actual cost is starting from the root node to the current node. That distance is denoted as Gn, which is called as the actual cost. And the distance from this current node to the goal node, this direct distance, it's not like we'll follow one path. No, the direct distance between the current node and the goal node is called as the heuristic cost or estimated cost or the utility cost of the node, we can say. Okay, so this formula is very important. To solve the AO star algorithm, we have to find out the cost for each node using this formula. F of n is equal to g of n plus h of n. And one important thing here we have to remember, by default g of n for any node is equal to 1. That means the distance from the root node to any node. So from here to here, or from here to here, or from here to here, any node, the edge value is 1. That is called as the Gn value. For every node, or Gn, like the actual cost is denoted as an, even if it is not given in our problem also, we need to consider that the actual cost of any node is equal to 1. Now, let me discuss about the AO star search algorithm. It requires a number of steps. So, step 1 says initialize the graph to the start node. Then step 2, traverse the graph following the current path, accumulating the nodes that have not yet been expanded or solved. Step 3, pick any of these nodes and expand it, and if it has no successors, call this value as futility. Otherwise, calculate only f dash, which is called as the heuristic value for each of the successor. And step 4, if the heuristic value is 0, then mark the node as solved. And step 5 says that change the heuristic value for f dash for newly created node to replace its successor by back propagation. Anyways, all these points I will discuss with the help of one example. And step 6 says, wherever possible, use the most promising routes, and if a node is marked as solved, then mark the parent node as solved. And step 7 says, if the starting node is solved, then or the value greater than the futility, then stop the process, else repeat from the step 2. This is what the problem I want to discuss, how we can solve this problem using AO star algorithm, and that too to satisfy this problem reduction method. Now in this graph, all the nodes represents the state over here, and here a number of nodes are given. S is the root node having 3 children, A, B and C, and under A 2 children are there, B, D and E. Under S, B only one node is there, or one child, that is B. Under C 2 children are there, F and G, and under D one child is there, F. And you can observe 2 arcs are present over here. One arc is here, another arc is here. That represents the AND graph. That means whenever we will solve this particular math problem, we have to consider that this is your AND graph. So to achieve now, what I can teach you, like how I can let you know, like here this as it is called as a AND R. So to achieve this S, we have to find out the value for this particular both the paths combinedly. But this is our OR path because there is no arc. So how to achieve S now? We either will follow this path or we can follow these two paths together. So that is up to your choice. But anyways, we have to find out the solution for OR path completely, and we will find out the solution for the AND path. Then we'll see which path provides the better solution. Okay, and in this diagram here, you can see here everywhere 1 is written, that is the value of GN cost, means the actual cost starting from the root node to any node, the edge value is given as 1. So from B, S to C, S to B, S to A, S to E, everything and A to E, A to D, everything it is given as 1. Now let me discuss how, and the orange color values, or which is given as with red color symbols, red color numbers, these are the heuristic values. Heuristic value means the estimated cost from the node, the current node to the goal node. So here it is given as 7 for heuristic cost of A is 7, heuristic cost of D is given as 5, heuristic cost of E is given as 6, like this. All these numbers are called as the heuristic value. Now as I discussed, we have to use the formula G of N, that is equal to H of, it's my bad, F of N, that is equal to G of N plus H of N. This is the formula we have to use to solve this problem. So Fn is the cost of every node. How we can find out? Using the actual cost and the heuristic cost. Now in this problem we have to achieve S. How to achieve S? As it is given clearly, either we'll follow the path S to C or we will follow the path A, S, B. So let us find out the cost of S to C path. What is the cost? So the formula would be G of C plus H of C. Why I am writing C? Why not S to C? Because whenever we are finding the cost, always you take care of the child node, not the parent node. Now G of C, that means the distance from the root node to C. What is the distance here? Every time G, anywhere I will write G means it is considered as 1, and H of C is given as 13. So 1 plus 13, it becomes 14. That means if I follow this path, the heuristic value of this S would be 14. Now I will solve this one because one AND arc is there. So F of A, S, B. So what are the children of S here? Two child, one is A, another one is B. So separately I will write G and H for A and G and H function for B. So G of A plus H of A, this is for A part. G of A plus H of A plus G of B plus H of B. Now what is G of A? It is given as 1. So 1 plus H of A is given as, the heuristic value of A is given as 7. Plus G of B, this distance is given as 1 and H of B it is given as 12. So 7 plus 1 is 8 plus 1 is 9, 12 plus 9 is 21. So if I follow this path, I am getting the value 21, cost of from S it will be 21, and if I follow this path, I am getting the cost as 14. Now what is the minimum cost then between 14 and 21? So definitely it will be 14. That means this path provides the optimal solution. But still now we have not solved completely. Again we have to follow, because some children are there for the C node. Here also under A node few children are there. So we have to solve those problems also. Then only we can find which one is the optimal one. So let me write over here. So till here we got like 14 and 21. Now right now the minimum cost for S is 14. Now we'll follow this path. As S to C path is providing 14. So that is why let us solve this part also. So in this part, C is the root node now. C is having two children, F and G. And the distance from C to G, F is 5 and C to G is 1. Sorry, C to F is 1 and C to G is 1. And the heuristic cost of F is 5 and heuristic cost of G is 7. Now how to achieve C? The same formula we will apply, F of F, C, G. We have to achieve C. as it is a and arc, so we have to follow the complete path. So we will find the cost of this complete path, then only we can achieve C. Then what will be the formula? F of f plus g of f, g of f plus h of f plus g of g plus h of g. Now what is g of f? It is given as 1, h of f is given as 5, g of g is given as 1 and h of g is given as 7. So 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 7 is 14. But what is the heuristic value of C is given here? 13. So now new heuristic value of C would be 14. So let us cancel this 13. Let me write 14 over here. Now, whenever we are calculating the new heuristic value for a particular node, the same value will be propagated to the root node also. So now let us recalculate the path cost of SC again. So what would be the cost of SC again? So G of C plus H of C. Because C value has been changed from 13 to 14. That is why we are calculating once again. So G of C is equal to what? That is 1. And H of C new value it is 14. So now it becomes 15. Okay. Now the new value, let me update for the S node. The heuristic value, revised value, I can write the revised cost for S node. It becomes 15 now. Now we will check for the left side also, because right side part is completed. Okay, so this one, it has been changed. Okay, now come to the left side part here. Now we'll take A as the root node. A is having two children, one is D, another is E. So both are OR graph because no arc is there. So separately we'll solve AD, separately we'll solve A to achieve the goal node A. Then we will find out which cost is minimum. Now let us find out the cost of AD first. So what is the cost of AD here? G of D plus H of D. What is G of D here? 1. H of D is 5. It becomes 6. Same thing F of A to E. That means the cost of A path would be G of E plus H of E. So what is G of E here? 1 plus H of E is 6. So 1 plus 6 is 7. Now you find out the minimum cost between 6 and 7. It is 6 only. But what was the cost it is given for the node A? So 7. Let us remove 7 and write 6. So now the revised cost for revised heuristic value for the node A becomes 6. As the revised cost is 6, again it to be propagated to the root node. So here and arc is there. So recalculate, complete the cost of ASB again. So let us calculate the cost of ASB, that is equal to, so we can write G of A plus H of A plus G of B plus H of B. So what is G of A? It is 1. H of A new cost, that is 6. G of B is 1 and H of B is 12. So now 6 plus 1 is 7 plus 1 is 8. 12 plus 8 is 20 now. So this side up to here we are getting the cost is 20, and here up to here we are getting the cost is 15. So if you compare 20 and 15, definitely 15 would be the minimum cost. Now again you might be thinking one more child is there under D. Should I solve that child or not? Actually, as per the AO algorithm, once we find different solution for both the parts, whether it is an AND graph or OR graph, then and if they differ from each other at the same level, that now you can see D, E, F, G. So all are in the same level. Up to this level, we got two values. One is 15 right side and the left side we are getting 20. Now we have to stop the process. I should not search again. I should not explore from D to H, because if I explore D to H, there will be imbalance solution we will get because there is no further exploration at the right side part. So if we find this type of case, then we have to stop the process. But when we have to move forward and we have to explore, if the solutions for both the sides at the same level, both matches or both are equal, then I will explore one more step further. Otherwise, we have to stop the process. So this is the solution. Our final solution would be 15. So we can follow. We have two solutions to achieve the goal node S. One is 15, another one is 20. But the optimal solution is 15, which provides by following the path SC, then CFG. So this is the path. So I hope you might have understood for this problem using Aeostar. This is the note I want to tell you when we should stop the process. That terminology is called as non-uniform depth. This term is very important in Aeostar. The problem arises because in an AND or graph, some parts of the solution might be deeper, which require more number of steps to solve than others. So when different subproblems have different depth levels, the Aeostar algorithm prioritizes the most promising path based upon the evaluation function. Evaluation function means the heuristic estimates. So these evaluation can lead the algorithm to focus on subtrees that look more promising at that time without resolving others that are at the different depth or level. Now let me discuss about few advantages and the limitations of Aeostar algorithm. Aeostar algorithm is actually complete because it provides the solution. We can at any cost we can achieve the goal. The cost may be high, but we can achieve. That is why it is called as complete, and will not go for any infinite loop. It will the searching process will not be repeated. Somewhere we need to stop, and less memory is required. It travels according to the ordering of the nodes. It can be used for both OR and AND graph. But the problem is it may not give the optimal solution as it doesn't explore all the path once it finds the solution. So that is why this is one of the limitation of Aeostar algorithm. So this is all about for this particular video lecture. I hope you might have understood about the problem reduction, how the problem can be reduced, and I explained two classical examples. One is the Tower of Hanoi problem, as well as I explained and I solved one problem using Aeostar. And for the preparation of this video, I have referred the Soros Kosick book for artificial intelligence. Even two websites for YouTube channels I have given. Those sites also I have referred. You can refer it. So thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.